Okay, let's get started. So today we're picking up where we left off last week with reductions and intractability. So remember, right, what's a reduction? So this diagram shows a reduction between decision problems. So we're given a problem A, for instance, alpha of problem A. And if we want to reduce, we want to use an algorithm that decides problem B in order to solve problem A. So we first put instance alpha through a reduction algorithm that converts it into an instance beta of the problem B. And then we use a polynomial time algorithm to decide problem B, right? It gives an answer either yes or no. And then that answer is also the answer for the instance alpha of problem A. So in order to show that this reduction is a polynomial time algorithm, so we need to show that the reduction itself runs in polynomial time, right? Converting the instance alpha of A to an instance beta of B. And then if alpha is a yes instance of A, then beta is also a yes instance of B, and vice versa. So it's yes instance of A if and only if beta is a yes instance of B. So these are the elements of reduction. Okay, last time we were talking about three sets, right? So that's a version of sets, so the satisfiability problem, where each clause contains exactly three literals. So like this formula, right? The first clause is x1 bar or x2 or x3. Right, second clause is x1 or x2 bar or x3. Third clause is x1 bar, x or x2 or x4, and there could be further clauses. What we want is that each clause is satisfied. Right? So every clause is satisfied. Like in each clause, there's at least one literal that is set to true. So satisfying assignment would be like x1 is true, x2 is true, x3 is false, and x4 is true. So this makes sure that in every clause there's at least one literal that is set to true. And this formula phi is a yes instance if and only if it admits at least one satisfying assignment. Right? As long as there's at least one way to satisfy this formula, then this formula is a yes instance of set. And I mean, you might wonder why 3, right? Why the number 3? Why not like 2 or 4 or 5 or some other numbers? Well, I mean, so first of all, what about one set? Right? So what one set would mean that every clause contains just one literal. Right? So it would be something like, so one set would be like, say, like x1 bar, right? So each clause just contains one literal, so like and x2, right? And x3 and x4 bar, something like this. And you can see that it's trivial, right? Because you're given a formula like this, then of course, like each clause contains only one literal, that has to be true. And then like this formula, you can satisfy it if and only if there's no variable that occurs simultaneously with this negation, right? So I mean, like if there's a one x1 and then like there's an x1 bar, then obviously this formula cannot be satisfied. Not like both of these cannot be true at the same time. But as long as there's no such situation where a variable occurs simultaneously with its negation, like in the formula above, right? X1 or x1 bar and x2 and x3 and x4 bar, and that's perfectly fine. You can set the x1 to false, x2 to true, x3 to true, and x4 to false. And this all clauses will be true. So I mean, one set, obviously you can solve it in polytime. Now two set, right now that gets more interesting. So two set, each clause has two literals. Yeah, that's less obvious, and turns out that still it can be solved in polynomial time. So we're not going to go into it, but I mean, you can look it up if you're curious. So three set is where it gets the problem gets hard. Right, so three set, there's no known polytime algorithm, and so that means that for higher set, right, 4 set, 5 set, and so on, that is also likely a hard problem. So that's why we're interested in 3 set in particular, like the number 3. So okay, this is an important problem in the study of complexity, and we'll see why later. But okay, we were talking about the 3 set, its reduction to independent set. Right? We want to show that 3 set can be reduced in polynomial time to the problem independent set. So we call it independent set. You're given an undirected graph, and you want to select as many vertices as possible so that no 2 vertices that you selected are connected by an edge. Right? So that's the independent set problem. So okay, to show this reduction, I mean, you have to start with an instance of 3 set, right, and then convert it somehow into an instance of independent set. So I mean, before we go into the reduction, I'd like to point out that at this point, I mean, it might not be even be clear kind of, like you might not have an idea like how to transform an instance of 3 set into an instance of independent set, right? These two problems seem like very different. 3 set is about the logic formula, independent set is a graph problem. So I mean, yeah, it's it looks like two problems. These are very different, like no relation, but actually there's a relation. Like you can reduce 3 set to independent set, and it goes as follows. So we start with an instance of 3 set, right? Instance formula phi. We create one triangle for each class, right? So the first class, remember, was the x1 bar or x2 or x3, right? So that corresponds to the first triangle in the picture here. And then second class goes to the second triangle, and then third class goes to the third triangle, right? So it's x2 bar or x1 or x3. That's the second class, and the third class is x1 bar or x2 or x4. So we have 3 triangles, and then we have these triangles. Then we connect literals, each literal to each of its negations. So you can see here that x1 bar is connected to x1, right? So by this line, and then again x1 bar, right, they're connected here by this line. And similarly, right, so x2 is also connected to x2 bar, and x2 bar is again connected to x2. So we add each edge whenever there is a literal as well as its negation. We connect these two vertices. And now there's x3, but there's no x3 bar, so no need to add edges there. And also there's x4, but no x4 bar, so no more edges. So this is the instance of independent set, right? Starting from any 3 set instance, you can create this instance, such an instance of independent set. Okay. And then for independent set, right, so we need a graph, and then we need the number k, right? What is the size, the target size of the independent set? So we'll set k to be the number of classes in the instance of 3 set. Right? So here there are 3 classes, so k is also 3. So we're asking whether there's an independent set of size 3 or more or not. That is, whether we can select the 3 vertices, no 2 of which are connected by an edge. Okay, so yeah, first we have to show that the reduction runs in polynomial time, right? Time polynomial the size of the input. And with most of these reductions, that's kind of easy to see, but still you need to state it. State that the reduction runs in this case linear time, right? You can take any instance of 3 set and then convert it into an instance of independent set using this reduction. And then okay, so how does the reduction run in linear time? Well, it's linear in the size of the input, right? So you create these, you're given an instance of 3 sets, so that's a formula. And so you're asking if we need to connect x1 to x1 bar and x1 bar to back to x1, right? So okay, it could be that there's a lot of x1s and lots of x1 bars. Yeah, I mean that's a good point actually. So yeah, I would say, yeah, maybe we should have written linear. So like let's say polynomial. I would say would be quadratic indeed. So that's a good point. I mean, it doesn't really matter for the correctness of the reduction, but because you might need to connect a lot of these edges, right? There could be like half, but maybe half the classes contain x1, like the other half also contain like x1 bar. Then you need to connect quite a lot of these edges to indeed. Yeah, but polynomial time. And okay, so what do we need to show next? We need to show that the instance of 3 set is a yes instance, if and only if the instance of independent set is a yes instance, right? So suppose first that the instance of 3 set is a yes instance. That means there is a satisfying assignment, right? We may assign like x1 to true, x2 to false, something like this. So what we do is we select a true literal from each class, right? So in each class, because it's a satisfying assignment, there must be a true literal. So we look at that vertex, right? We take that vertex. So in this picture, we're taking like x2 from the first class, and then x3 from the second class, and then x2 again from the third class. right? So we select the right, each clause there must be at least one literal that's set to true. Now, I mean, there could be more than one. That's fine. I mean, we just take one, just take an arbitrary one. Now we claim that the corresponding k vertices must form an independent set in the graph, right? So why is that? Well, so first, that we only pick one vertex from each triangle, right, from each clause. So no two of these vertices will be connected by the edge of one triangle because they belong to different triangles. And can it be that that we select something like x2 here and we also select like x2 bar here? It cannot, right? Because if we select both x2 and x2 bar, that would mean that we set x2 to true, and we also set x2 bar to true, right? And that's that's wrong. I mean, that's a contradiction. We cannot set both of these to true. So we'll never choose two vertices that are connected by an edge, like crossing different triangles, right? Because that would mean that we set some variable to true and also its negation, some literal and its negation both to true, and that cannot happen. So indeed, the k vertices that we've selected in this graph form an independent set, right? So no two of them are connected by an edge. Okay, the other direction, we have to show that if the instance of independent set is a yes instance, right? So that means that there are k vertices that form an independent set, then the original instance of 3SAT is also a yes instance. So, okay, I mean, the reasoning is similar, right? Suppose it's yes instance, we can choose k vertices that are no two of which are connected. So first of all, like all these k vertices must belong to different triangles, right? Cannot be that two of them are in the same triangle because in each triangle, like any two vertices are connected. So that means that because they're exactly k triangles, so these k vertices, like there's one per each triangle, right? For each triangle, we've picked one vertex, and note that any of these two vertices cannot be connected, right? That's because it's an independent set. So if we set these literals that we've chosen in each triangle to true, then all clauses will be satisfied, right? So here we set the x2 to true, right? From the first triangle. We choose the x3 to true, and again we choose the x2 to true. So x1 and x4 can be anything, doesn't matter. Okay, but already this choice ensures that every clause will be satisfied, right? Because there's at least one literal that's set to true. And the independent set property guarantees us that we're not going to run into trouble, right? We're not going to run into the contradiction in the sense that we try to set x2 to true and also try to set x2 bar to true, right? That will never happen because if we try to do that, then these two edges, these two vertices must be connected by an edge, and the set of vertices that we've chosen would not be an independent set. So we'll never run into a contradiction when we try to set the values of these variables to true or false. Okay, so that's the reduction from 3SAT to independent set. So any question about this this reduction? Okay, so yeah, so we've shown, right? So last week we looked at independent set to vertex cover, right, and also vertex cover to set cover, and now we did the 3SAT to independent set. Now, I mean, there are all these other reductions in this diagram, like 3SAT can be reduced to a subset sum or a directed Hamiltonian cycle, and so on. So we have the relations between all these problems. So what have we shown, right, from this diagram? We know that because 3SAT can be reduced to all these problems, remember that polynomial time reductions are transitive. So if 3SAT doesn't have a polytom algorithm, then none of these problems would have a polytom algorithm, right? That's because of these reductions, right? If any of these problems have polynomial time algorithm, that would imply a polytom algorithm for 3SAT. So, okay, I mean, why do we care about this? There are many reasons why we care, but one of them is that the problems that are believed to be hard are the basis of secure crypto systems, and so like there are systems out there that rely on the hardness of these problems, and there's the entire area of complexity theory that's devoted to comparing the hardness of different problems. So that's an important area in computer science. But I mean, if you think about this, right? So this implication says, okay, if 3SAT doesn't have a polytown algorithm, then none of these problems would have polytown algorithms, right? I mean, that's fine. But what if someone finds that like an order n squared term algorithm for 3SAT tomorrow, right? Then what would we have from this implication? We would have nothing, right? Because this implication is based on the assumption that 3SAT does not have a polytown algorithm. If there's a polytown algorithm, then these reductions so far would tell us nothing about other problems. So if there's an efficient algorithm for 3SAT, then these implications would tell us nothing about the hardness of other problems. So it seems dangerous to say that all these problems are hard just based on the lack of progress of this one specific problem, right? For 3SAT, right? Maybe like 3SAT is actually not that hard. But it turns out that our situation is what we can say is much stronger than that. And in particular, there are also reductions back from these other problems to 3SAT, right? So it's not just that there's reduction from 3SAT to all these other problems. There are reductions the other way as well. And there's no polytown algorithm known for any of these problems. So these like problems. So not just on this, not just on this diagram, but also the other like hundreds and thousands of problems. Several of them are encountered routinely in applications. So all these problems are computationally equivalent to 3SAT, right? Because of these reductions back and forth. So if there's a polytown algorithm for any of these problems, then that would imply a polytown algorithm for all the other problems. Or equivalently, right, conversely, if you believe that any of them is hard, right, if you believe that the vertex cover is hard, that would imply that all these problems are hard, right? So all these problems in this diagram are hard. So the blue arrows, I'll go into that later, but it's just the direction backward that other problems can be reduced to 3SAT. So it follows from what's known as the Cook-Levin theorem, so which will be covered in the later in this lecture. Okay, so that brings us to the topic of complexity classes, right? So these class P, NP, and so on. Yeah, so first let's start with the easiest one, right? That's class P, right? So P is a set of class or set of problems that can be solved in deterministic polynomial time, right? So problems like sorting, right? Sorting can be solved in n log n, or other problems that we've covered, so like minimum spanning tree, right? So minimum spanning tree, we've talked about that in the lecture about greedy algorithms. So that's can be solved in polytom. Or what else? So like longest common subsequence, right? Longest. That can be done by dynamic programming, or fractional knapsack. Can be done by a greedy algorithm. So all these problems are in P, right? They can be solved in time polynomial in the size of the input. So we know several problems in P already. But okay, the next thing is NP. Right, so what's NP? So okay, NP doesn't stand for not polynomial. It stands for non-deterministic polynomial, and that's a class of problems for which for some of them, we don't know whether polynomial time algorithm to solve them exists or not. But for yes instances of them, of the problems in NP, there are polynomial time verifiable certificates. So there are certificates that allow you to verify in polynomial time that these instances are indeed yes instances. Now, okay, like why the name non-deterministic, right? So there's like an equivalent definition of NP, and that's the class of problems that can be solved in polytom by what's known as a non-deterministic Turing machine. So it can be solved, but by a non-deterministic Turing machine, and that's where the name comes from. But yeah, that's not so important. What's important is that the main definition is that this class of problems for which there are certificates that allow you to verify in polynomial time that the instance is a yes instance. Okay, so let's do some example. So remember subset sum. Right, so in subset sum, we're given a list of integers and a target number like t, and the problem is to decide whether there's a subset of that set that sums up to t. Right. So for example, like maybe you have let's say so S is say 2, 4, 5, 6, 8, and 10, and maybe T is 17. So you want to know whether there's a subset of these numbers that sum up to exactly 17, right? Now, I mean, there's no polytom algorithm known for subset sum, but if you just want to verify that this instance is a yes instance, right? If I want to convince you that this instance is a yes instance, I can just show you the certificate. Right? So what's a certificate? Certificate would be just the list of numbers that that really sum up to T. Right? So in this case, I would show you like 2, 5, and 10. I tell you these 3 numbers, and you can verify yourself, right, that these indeed add up to 17. Right? And you can check that, okay, these numbers really that really appear in S. So these 3 numbers form a certificate, right? This subset S prime that sums up to T forms a certificate. You can verify in polynomial time that these numbers sum up to 17 and exist in S. So by this reasoning, the subset sum problem belongs to NP, right? So it is in NP. So by this certificate. Okay, another example, Hamiltonian cycle. So Hamiltonian cycle, you're given a graph, and the problem is to decide whether there's a simple cycle, which is a cycle that doesn't repeat the vertex or edge, right? And you want it to visit every vertex in the graph exactly once. Okay, so you might be given a graph like, so maybe this, let's say, this, these 6 vertices, let's say like 1, 2, 3, 4, 5, 6, and you want to know whether there's a cycle that visits all these 6 vertices, and each of them exactly once, and then it's a cycle, so it comes back to the original vertex, right? So I mean, again, like Hamiltonian cycle, there's no known polytom algorithm. But if you just want to verify that this is a yes instance, what I can show you the certificate, and that's the cycle itself, right? So I can tell you, oh, like go in this order. So let's say like 1, 3, 2, and then 5, 6, 4, right? And then back to 1. So you can check, right? You can follow this in this graph, okay, 1, 3, 2. 5, 6, 4, 1, right now. Okay, so it visits every vertex once and goes, never repeats a vertex or edge, and goes to all vertices. So that's indeed, this instance is a yes instance, right? Because of the existence of this cycle, and you can verify this in polynomial time. So this means that the Hamiltonian cycle belongs to NP. Right, because there's a certificate that allows you to verify in polynomial time that an instance is a yes instance. Okay, so that's the definition of NP. And so for most of these problems in NP, there's an easy certificate. So that's usually like the kind of the solution itself, right? So here, like the certificate is the cycle itself, or like subset sum. It's like the subset itself that adds up to T, like that serves as the certificate. If you have the solution in hand, you can verify efficiently, right, in polytom that it is indeed the correct solution. So solving it might be difficult, but verifying it for yes instance is easy. Now, okay, I claim that any problem in P is also in NP, right? So any problem like sorting, minimum spanning tree, longest common subsequence, things like this, is also in NP. So why is that? Well, that's because the certificate can be anything. If you have a problem in P, then the verifier doesn't even need to bother about the certificate. The verifier can just solve the problem by itself, right? And then check whether it's a yes instance or not. Because the problem is in P, so it can be solved in polytom. And so instead of trying to verify the certificate, why not just solve it to solve the problem? Because the whole problem is easy, right? Solve the problem, and then it can verify that, oh, yeah, this is indeed a yes instance. So any problem that's in P is also in NP, right? So P is a subset of NP. Okay. Now, okay, why NP? Right. So NP, it captures natural search problems. Right. So it's similar to searching for a needle in a haystack. Right. So if someone gives you a haystack and asks you, oh, is there a needle in this haystack? It's probably hard for you to answer hard for you to know for sure, right? You need to like search very carefully. That's very hard. But suppose that person goes into haystack and then picks out a needle and shows you the needle, then now you know for sure that this instance is a yes instance, right? That there's a needle in the haystack. So you're convinced because of the existence of that certificate. And it's easy for you to verify that the certificate actually works, that it's indeed a needle, right? So that's why NP, right, it really captures several search problems out there where it's kind of hard like to search for the thing, but once you have the thing, it's easy to check that that thing works. So that's the kind of why NP is a natural concept to capture these problems. Now, okay, next is the NP hardness and the NP completeness. So, okay, NP hardness, so here's the definition. Now, problem A is said to be NP hard if for every problem B that belongs to NP, B can be reduced to A in polytom. Right, so what does that mean? Right? Remember, like if B can be reduced to A in polytom, that means A is at least as hard as B, right? That's the implication from this reduction. So here it says that A is at least as hard as B. So A is at least as hard as every problem in NP. Right? So that's the implication. So A is at least as hard as every problem in NP. I mean, A could be much harder than every problem in an NP. Could be like every problem in NP could be harder, or could be like equally hard as the hardest problems in NP. This is what's known as NP hardness. So again, this is a class. So all these concepts are classes of problems. Right? So P is a class of problems, NP, and then now we have NP hard and NP complete. So each of these is a set containing like several computational problems. So NP hardness is at least as hard as every problem in NP. And then NP completeness, so a problem is said to be NP complete if, like two things, right? If it's in NP and it's also NP hard. So it's like the hardest problems in NP, right? For NP completeness, we know that this problem is in NP, and at the same time it's NP hard. So it's at least as hard as every problem in NP. So that means that this problem is the hardest problems, right, among the hardest problems in NP. Yeah, so there are problems that are not in NP, right? So there are problems that cannot even like be solved in finite time. So one like well-known example is what's known as halting problem. You can look that up. But yeah, I mean, it's not like every problem is in NP. So there, even though like from the examples like the Hamiltonian cycle or subset sum, you may think that any problem, even if it's hard to solve, it should not be hard to verify yes instance, but that's not true. There are problems that even like verifying could be like very hard. Okay, so this is the definition of NP hardness and NP completeness. Now, okay, right, we talk about this NP hardness and NP completeness. So what problems really belong to these classes? So there's a theorem that due to Cook and Levin. It says that any problem, like so every problem in NP, can be reduced in polytom to 3 set. Okay, so any problem that belongs to NP can be reduced in polynomial term to 3 set. And so if you follow this definition, right? So this statement and the definition of NP hard, it says every problem in NP, right? Problem A is said to be NP hard if for every problem B in NP, B can be reduced in polytom to A. Right now we here the statement says any problem in NP, polytom reduces to 3 set. So that means that 3 set is NP hard, right? By definition of NP hardness. And 3 set is also an NP complete, right? Why is that? Remember, NP complete means that it's NP hard and in NP, right? We know it's NP hard. The 3 set is also in NP. Again, that's not the reasoning is just the certificate of for 3 set would be just the satisfying assignment itself, right? So saying that x1 is true, x2 is false, x3 is true, and so on, like this satisfying assignment. Once you have that, then once you have a certificate, then you can check whether it really works or not. Check whether the formula is satisfied by this certificate or not. So that would mean that the 3 set is also NP complete. So this is the importance of 3-SAT. This is why in the diagram it appears as the first problem. It's because 3-SAT was the first problem to be shown to be NP-complete, right, by this Cook-Levin theorem. And once we have this, you don't need to understand where this theorem comes from. Just know the statement that 3-SAT is NP-complete. But once we have this theorem, what we know is that for all these other problems that we've talked about with these reductions, these other problems are also NP-complete. Right? That's because there's the reduction both ways to and from 3-SAT. Right? So these problems subset sum, vertex cover, independent set, and so on, because these problems are computationally equivalent to 3-SAT, these problems are also NP-complete. Okay, so back to this diagram. So we have P, we have NP, right? NP, that's the problem that polytime reduced to 3-SAT. So problems that are at least as hard as 3-SAT. Reduced to 3-SAT. So the problems that are no harder than 3-SAT. And then NP-complete is problems that are computationally equivalent to 3-SAT, right? So these are the hardest problems in NP. So we know that P is a subset of NP and also NP-complete. That's a subset of NP. But it could be that all these circles are actually the same. It could be that all these sets are actually the same set. So whether that's true or not, well, no one knows. Right? So that's an open problem, and it's probably the most famous open problem in computer science. So there's a big prize if someone can solve it, whether P is equal to NP or not. And so many people have speculated different things. It's a really fun topic that computer scientists like to talk about, this P-NP conjecture. Still, no one knows. So most people believe that they're not equal, right? Because all these hard problems, if P equals NP would mean that right, every problem in NP can be solved in polynomial time. So all these problems like SAT, vertex cover, subset sum can be solved in polytime. And since there are many of these problems, and no one knows any polytime algorithm for any of them, it seems unlikely that there are polytime algorithms for these problems. So that's why people, most people believe that P is not equal to NP. So no one knows the answer for sure. But what we know for sure is that NP completeness is a very important concept in computer science. So it's used in many publications and many books and so on. And it's a very important tool for showing that a problem is hard, right? It's computationally hard, or it's likely to be computationally hard. Right? I mean, so imagine, suppose maybe some time from now, you encounter a new problem, maybe in your research or in your work. You try to solve it, right? I mean, maybe you try to apply some of the paradigms we learned in this module, right? Like greedy algorithms, dynamic programming, or divide and conquer. So you try to come up with a polytime algorithm, and you don't succeed. So suppose you try hard, but you don't manage to come up with a polytime algorithm. Then you tell someone else that, oh, this problem is probably hard. Probably there's no polytime algorithm, because you've tried hard and you spent a week on it, and then you didn't manage to come up with a polytime algorithm. Now that's other people are probably not going to be convinced by that argument. Right? Maybe you're just not you don't have the right insights to solve that problem, or maybe you haven't tried hard enough. Right? Maybe that's what they'll tell you. But if you can show that your problem is actually NP complete, right, by reducing from some other NP complete problem, then that's a much stronger argument, right? Because now what you've shown, right, is that if there's a polytime algorithm for your problem, there would be a polytime algorithm for all these hundreds of thousands of problems in different domains that people have tried solving for many decades, and no one has found a polytime algorithm for any of them. So if your problem is NP complete, then it's quite likely that it's really computationally hard. Right? People are much more likely to be convinced. So that's why NP completeness is important. Right? It's a way for you to show that a problem is likely to be computationally hard. And so there's a classic book by Gary and Johnson, Computers and Intractability. So it includes a long list of NP-complete problems, like over 300, and it's very well cited. And you can imagine this because whenever you need to show, you want to show that a problem is NP-complete, you need to reduce it from some NP-complete problem. Right? So it helps to know a lot of NP-complete problems. So this book is important because it contains like many of them from different domains, which you can try to use as a starting point to reduce to your new problem, right? So that's why this book, even though like it's several decades old, is still very much in use. Like people use it regularly, including me. So yeah, NP completeness is important. And yeah, now suppose like you've shown that a problem is NP complete. Does that mean that it's completely hopeless, like to solve that problem? You just give up, like just not implement any algorithm for that problem? Well, no. So there are some ways to deal with NP completeness. So let me mention a couple of main ways that people use to deal with when a problem is NP complete. So first is to approximate, right? To use approximation algorithms. So what does that mean? That means that you find an approximate solution in polynomial time, right? So for example, like vertex cover, right? You want to cover the cover all the edges using as few vertices as possible. So that's an NP-complete problem. So probably there's no polytime algorithm to solve it exactly. But if you're fine with the answer not being like exactly optimal, right? So maybe you select a few vertices too many, but it's still a vertex cover, and like not too many vertices more than the optimal solution. If you're fine with that, then you can get polytime algorithm. Actually, there's a simple greedy algorithm for vertex cover that gives a two approximation. So that means that the vertex cover that this algorithm finds is no more than twice as large as the optimal vertex cover. So it's like the graph could be like 1,000 vertices, maybe optimal vertex cover has size 20. Then solving for the optimal vertex cover might be hard, right? But this algorithm is going to give you some vertex cover that has size no more than 40. So no more than twice as large as the optimal vertex cover. No, you give up give up something in terms of optimality, but in return you get the polytime algorithm. So there's a huge literature, like one whole area of computer science of approximation algorithms. So finding approximation algorithms for different problems. Okay. Another way that people use to deal with NP completeness is to use heuristics and exploit structures in typical inputs. So one classic example of this is SAT. So not just 3 SATs, but 4 or 5 or like larger SATs. So like each clause could contain many literals. So SAT is of course like 3 SAT or more is already an NP complete problem. So you shouldn't hope to solve it in polytime, like solve every instance. But actually, modern SAT solvers can solve even relatively large instances quite fast. And that's not a contradiction. That's because what they do is they use heuristics, or they have ways to deal with the typical inputs. So even like instances with hundreds or thousands of clauses and variables, or like sometimes even millions, these SAT solvers can solve them relatively fast. However, if because the problem is NP complete, right? If you really try to break like a SAT solver, right? Given a SAT solver, you really try to make life difficult for it. You can come up with maybe a formula with hundreds or thousands of variables that makes the solver like run for a really long time. That makes, because if you try to like make the heuristics not work, right? Try to break kind of the solver, then you can. But yeah, so there's a whole community of people, of researchers that work on SAT solving. So in our department, like my colleague Kuldeep Meal, so he's an expert on SAT solving. So he and his team have built SAT solvers and participated in SAT solving competitions. So there's a whole area about this, because SAT is so important, right? It's a fundamental logic problem. It's like kind of the canonical, like most well-known NP complete problem. So that's why it's so like there's so much intensive research on that. And yeah, you can use for most inputs like that appear in the real world, there's going to be some structure, or at least for inputs that are not adversarially constructed, there are ways that you can exploit in order to solve it quickly. that, even though it's an NP-complete problem, in practice, it can be solved relatively quickly. Okay, so this slide is beyond the scope of this module, so I just put it here just to give you an idea of what's beyond NP completeness, kind of what tools, what approaches you can hope to use if your problem is NP complete. Okay, so actually that's all of the content. So before I move on to the logistics and talk about the final exam, so any questions? Yeah, okay, so linear programming is another good example. So linear programming is in P, right? So there's a polytom algorithm to solve linear programming. Yeah, so yeah, maybe shouldn't talk too much into go into that, but kind of yeah, in practice, it can also be solved quite efficiently. Yeah, linear programming. So it's not yeah, even though like of course it's a very general problem, but also like there's a way to there's a way to solve it efficiently. But there's also a polytom algorithm, but polytom algorithm is not the way to solve it efficiently, most efficiently in practice. So sometimes there's a difference between like efficient kind of in theory and efficient in practice. Okay, any formal relationship between NP completeness and time complexity? Well, so NP completeness means that it's unlikely that there's a polytom algorithm. So if there's a polytom algorithm for any NP complete problem, right, that would mean there's a polytom algorithm for all of them, and that would mean that the P equals NP. Non-deterministic Turing machine. Yeah, I don't want to go into that really. I mean, just yeah, this is a technical point. This kind of Turing machine that tries different solutions that can do it kind of at the same time. What's for lecture next week? There's no lecture next week. So next week is the NUS Wellbeing Day. So there's no. This is the last lecture. Okay, so yeah, let me go on to the rest of the stuff. So what do we have left in this this module, right? So we have assignment 10, so that's due this weekend. Assignment 11, that's right one more weekend from now. Assignment 12 is cancelled. Programming assignment 2, that's optional, very similar to programming assignment 1. It has been posted. And that's due on April 21, so that's 2 weeks from now, Thursday of reading week. And final exam practice questions, I'll release them tomorrow. There will be a review session to go over these questions during reading week, so on Wednesday on Zoom, just like for the midterm review. So we'll send out a Zoom invite closer to the date. And the final exam, so that's Tuesday, April 26th, so 5 to 7 p.m. Logistics is essentially the same as midterm. I just uploaded to Luminous. And so it's like, yeah, essentially everything is shifted 3 hours later. Right? Midterm was 2 to 4 p.m., like final exam 7. Everything shifted 3 hours later. The format of the exam itself is also, will also be similar to the midterm. And from the material before the midterm, right, to help you with the review, not to spend too much time, only material from lectures 2 and 3 will be tested. So lecture 2, that's remember that's asymptotic notation, right, comparing the running time of different expressions. And lecture 3, that's about solving recurrences and divide and conquer. So if you missed questions from the midterm about these topics, be sure to review for the final exam. And of course, like everything after the midterm can be on the final exam. So a suggestion, like, make sure to review assignments, tutorials, and final some practice questions. So just like the midterm, I'll put in some questions that are variations of questions from these that you've seen before, like from assignments or like other components of the model. So I recommend that you review these carefully. So make sure not just to understand the question and solution itself, but if there's like some kind of variation, then you can solve these as well. Okay, let me give some more concrete hints. So yeah, let me tell you right away, there will be a question that asks you to show that that a certain problem is NP complete. Okay, so let's call it problem X. Right? You'll be asked to show that this problem X is NP complete. So what are the components, right? What are the steps that we need in order to show that X is NP complete? Well, so remember, NP complete, that's two things, right? That's the problem is in NP and it's NP hard. So first, you should show that X is in NP. Yeah, I suggest you start with this. This belongs to NP because it's usually the easy part. And question that will be no different. What does that mean, right? As it is in NP, so that it means that a yes instance should have a certificate that can be verified in polynomial time, right? So we've seen that for a subset sum and for Hamiltonian cycle. So any yes instance has a certificate that can be verified in polynomial time. So that usually that certificate is just the solution itself. Once you have the solution, you can verify that it works in poly time. Okay, so make sure that you don't miss the first step. And then the second step, which is the more interesting step, right? That's to show that X is NP hard. Okay, so what does it mean to show that X is NP hard? So this is right. In order to show that X is NP hard, you have to reduce from another NP hard problem. Right, let's call it A. Right now, make sure to get this direction right, because if you get the direction wrong, then it doesn't matter what else you do. Like this reduction is your reduction is going to be wrong. Right, so you have to start with another, right, a different problem. Right? I mean, it's tempting. Like you want to show that X is NP hard. Maybe you want to start with X and like do something, but that's wrong. You have to start with an instance of another NP hard problem A. And now, like in real life, like this is one of the kind of interesting part, like which NP hard problem to reduce from, right? And that can require like experience, and knowing a lot of NP hard problems. But in the exam, I want to avoid this stuff, so I will tell you like which problem A to reduce from. I'll give you this problem A with its full definition, so you don't need to worry about which problem to reduce from. So usually, like in real life, you try to choose some problem that seems similar to X, right? That seems related, and that you could imagine transforming an instance A to an instance of X. But sometimes the reduction itself can be quite complicated. But yeah, that's you don't have to worry about that. So the problem A will be given to you. I mean, this is why the Gary Johnson book is so useful, right? This book with like more than 300 NP complete problems, because it gives you a whole list of problems to choose from. In the exam, I'll tell you which problem to reduce from. Now, what do you need to do for the reduction? So the reduction should convert any instance of A into an instance of X, right? That's what the reduction should do. You start with any instance of A. This reduction should turn it into an instance of X in polynomial time. Now, okay, you start with an instance of A, right? So, like if A is say subset sum, right? That the instance would be a list of numbers in the set, and that the target number T, right? If A is the vertex cover, the input instance would be the graph, right? And then a number, kind of target number, whether you can cover all edges using, say, at most 10 vertices or not, right? So that would be the instance. You have to start with an instance of A and convert it into an instance of X. Okay, so now, yeah, let's be clear, right? So when you start with an instance of A, what you're not trying to do, you're not trying to solve the instance of A directly, right? You're not trying to solve this instance of, say, subset sum or like vertex cover. I mean, that's likely to be that it's likely that there's no polytop algorithm for that, right? So that's not the point of the reduction. And the reduction should not depend on whether the instance of A is a yes instance or a no instance. Yeah, you should not say like, oh, like if subset sum, if there is a subset that sums to T, then you do this. If there's no subset that sums to T, then you do this. or if you start with like SAT, it should be not, you should not say like, oh, if there is a satisfying assignment, then the reduction does this. If there's no satisfying assignment, then the reduction does that. It should not depend on this, because the problem A itself is NP complete, right? So it's likely that it's likely that there's no polytom algorithm. That's not the point of the reduction. The point of the reduction is just to convert an instance of A into an instance of X, regardless of whether the instance of A is a polytom, so is a yes instance or a no instance, right? So the reduction, like as we've seen, should not depend on whether the instance of A is yes or no. Okay, you just want to do this conversion. Now, okay, to show this reduction is valid, what do you need to show? So first, you need to show that the reduction runs in polynomial time, right? If this, most for them, I mean, like I think for pretty much all the reductions that we've covered so far, I mean, this is true. This is true for many reductions out there, and it will be true for the reduction in the on the final sum. So if this is clear, you can just say this. Yeah, you can say that clearly the reduction runs in polynomial time. That's fine, but you have to say it, right? If you don't say it, you'll get deducted, because it's one component of the reduction, right? That it runs in poly time. And then then it's the if and only if, right? Yes, if and only if. Yes. So if the instance of A is a yes instance, then the instance of X is also a yes instance, and vice versa. Right? If the instance of X is a yes instance, then the original instance of A is also a yes instance. So you need to show these three things, right, in order to show that your reduction is correct, is valid. Now, okay, I mean, when you start with an instance of X, right? I mean, of A, it might not be clear. Okay, how do you convert it to an instance of X? So my suggestion would be, if you're not sure how to start, at first, try something trivial, kind of see like how you can use the information in that instance, like to convert it to an instance of X, and see whether it works, right? See whether it's true that instance, right? It's a yes instance if and only if instance of X is also a yes instance. And if it doesn't work, let's see how you can fix it, how you can make it so that the instance, it's a yes instance is this if and only if relation. And probably if you're not sure, your best bet is probably to review reductions from that you've seen from in this module, like from lectures, from assignments, from tutorials, and also maybe some in the final exam practice questions. So review these reductions. It will give you an idea of like how these reductions work, and of how you can convert an instance, right, from one problem to an instance of another problem. And I mean, the reduction that I'll ask in the exam will not be more difficult than these reductions that you've seen in the module. So it's not my point to put something that's more difficult, that you have to come up with a complicated reduction. Right? The main point is that you know all these steps of showing that the problem is NP complete, and that you can come up with at least a simple reduction by yourself. So that will be there will be one question about this. Okay. And then the other thing, right, the other hint I want to give for the final exam is that this issue of input representation. So we've talked about it quite a few times already, but I know that it's kind of can be confusing to some of you. So I want to make sure again, like that you should understand why is the knapsack dynamic programming algorithm, why is this not a polytom algorithm, right? I mean, the algorithm runs in time order n times w. So remember knapsack, right? That there's n items, and then you're trying to fit choose some subset of them, like with total weight at most the capacity capital W of the knapsack, and you want to maximize the value of these items. The algorithm runs, dynamic programming algorithm runs in time order n times capital W. But why is that not I mean, it looks polynomial, but it's not polynomial, right? Because the input has size only order n times log of W, right? That's because number W can be represented using log of W bits. So the running time of the algorithm, it's not polynomial in the size of the input. So make sure you understand this point, okay? That's all the hints I want to give. So, and also, believe it or not, so that's also all for this module, at least as far as the lectures are concerned. So one thing, right, please fill in the student feedback survey. So thanks to those of you who've already done that. So it's an important way to make sure that let the university knows that the module was run properly, and like things like lectures, assignments, tutorials took place as they should. So please fill that in if you haven't already. And of course, like good luck with the final exam and beyond. Okay, so that's it. And yeah, I'll stick around for questions. Okay, can we claim that polynomial means polynomial to the in the encoding of the input? Yeah, I mean polynomial in the size of the input. Yeah, that's pretty much, I mean, always like what it means when we talk about running time. Binary search runs in log n, not in NP. So binary, I mean, any problem in P is in NP, right? Remember that. So binary search, I mean, is in P, so it's also in NP. Why is it n log w and not n plus log w? Yeah, I think it's yeah. I mean, writing n plus log w here should also be correct because n is the size of so the items. Each item you're given the value and the weight. Right? The w itself is a number. So yeah, if you write big O of n plus log w, yeah, that's also fine. I mean, I just write n log w because that's simple, and big O means at most anyway. So yeah, but that's a good point. N plus log w would also be fine. Why n log w is not polynomial? Well, so what's not polynomial is, right, so this w is not polynomial in log w, right? So write that. This like w is not polynomial log w, right? Because the size of the input is like depends on log w, but so if something runs in time w, that's not polynomial in the size of the input. The blue arrows. Yeah, I mean, the blue arrow, I mean, on slide 13, that doesn't kind of carry extra significance. I mean, the arrows, because we talked about this reductions, right? I mean, these blue arrows, you know, they follow from the Cook-Levin theorem. So, you know, it says that you can reduce any problem in NP to 3 set. But I mean, yeah, kind of that's not like an important point that I try to make with these different colors. But isn't log w less than polynomial? Well, I mean, yeah, that's the thing, right? So what the polynomial depends on polynomial in what, right? If log w is less than polynomial in w, but for knapsack, right, we're trying to, right, because the size of the input, right, when you're given a number w, when you're given a number w, the size is log w. Yeah, so indeed the encoding size is log w. So running time is exponential in the encoding size. Okay, so if you have a problem that takes OW to solve, where W is an integer, but you require log W bits to encode, it is not polynomial in the size of the input. Yeah, that's correct. Because if input has size that's log W, you take time W, I mean, that's not polynomial algorithm. And I mean, yeah, this is clear if like, you know, this kind of point should be clear if you think about like, yeah, I think I gave this example, right? Say you have a number like say 64, like, you know, or like, yeah, even like 100-bit number. Oh, sorry. I think, yeah, you have a number given like bits, something like this. It's like say like yeah, 100 bits, right? So to encode this, you just need 100 bits. I mean, it's not a lot of space, right? You can just encode it. But if the algorithm, if your algorithm runs in time, like the value or in the order of the value of this number, where this number is like 2 to around, like could be up to 2 to the 100, right? Because 100 bits. You have an algorithm that runs in time 2 to the 100. That's a really like a huge amount of time, right? You're not gonna finish it like in any like this is like way beyond like many years. So there's a difference between like log W and W. So like here, the value of the number would be W would be 2 to the 100. But in order to encode it, to encode a number this large, you just need the 100 bits, right? So log W is 100. This is why, like we say that if the input has size log W, then an algorithm that runs in time W should not be considered a polynomial time algorithm, right? Because here, like log W, and the size of the input is not that big. I can write like this, the 100 bits to you. I can type it to you in like 30 seconds. But if your algorithm runs in time order W, then you're not going to finish it in any number of years, like anytime soon. Is n also represented using log n bits? So if the number n is given as an integer, then yes, it would be represented using log n bits. But if you talk about kind of say you're talking about sorting, when you're given an array like a1, a2 to an, then the size of the input here, right, the size of input would be order of n. So assuming that each of these numbers is not that big, then the size of the input would be order n, so, and not order log n, right? That's because like for each already like each of a1, a2, and so on, you need to write down something to represent it. So already for sure you need to spend space like n. So size of the input of like a1, a2 through an, like this whole like list of numbers would be order n. But if you're just given like the number n, then the size of input would be order log n, as you mentioned. Okay, can you assume that whenever we use integers, we need to consider it as encoded in bits? Yeah, so usually like if an integer is given like as a standalone input, then indeed, yeah, then you can assume that it's encoded in bits. So like a number W, like you would take a space log W to represent it, to encode it.
Prof, can I ask a question? With regards to the reduction of the tree set to the independent set reduction to tree set reduction to independent set.
Yeah.
Yeah. For the beginning of the slides, it's like I don't see how the proof shows that every case will be like that. So it's like the suppose phi is a yes instance, take any satisfying assignment for phi, select true literal for each clause. Then corresponding K versus form an independent set tree. How do we know that it is true for every single phi?
Yeah, it's true for every single phi that's a yes instance, right? Suppose you're given a yes instance, so that means that there is a satisfying assignment, right? Say like the satisfying assignment might set x2 to true, x3 to true, x1 to false, x4 to false, something like this, right? And we say that if there's a satisfying assignment like this, then we can construct, right, in the converted instance of independent set, we can construct k vertices. We can choose k vertices that form an independent set, and that's by this argument on this slide, right? That's because these k vertices, because we choose one vertex for each triangle, so these k vertices are from different triangles, so they're not going to be connected by edges within a triangle, and then they're also not connected by edges across different triangles, because we'll never choose like x2 and x2 bar simultaneously. That will mean we set x2 to true and x2 bar to true. So like it cannot be that we choose like both x2 and x2 bar. So these k vertices will indeed form an independent set.
I see. Okay, just curious. For this particular example, right? If let's say x4 is also set to true, then wouldn't that not be an independent set anymore?
Right. So in this when we choose the k vertices, we just choose one. When we say like select a true literal from each class, right? So we just, if there are several of them, we just select one. So in one class, we just choose one. So it could be that say f2 in the third class, like f2 is true and f4 is also true, right? We don't want to choose both. Yeah, as you said, if choosing both would be bad. We will just choose one. So here we in this diagram, in this figure, we're choosing f2. We could also like not choose f2, say we choose f4 instead. We say like both x2 and x4 are true. We said like from the third class, we choose x4, right? We select the literal x4, which is true. And then we also, we're again fine. We're left with the f2, f3, and x4. This is also an independent set.
I see. So it is how to describe it? It is that because so long as one of them satisfied, then it will prove it. So that's why you don't, if let's say both x2 and x4 are both true, you just need to pick one and it will be sufficient to prove the case already.
Yeah, I mean, well, I mean, here you're starting with a satisfying instance, like say x2 and x4 are true, and you're converting it into an independent set, right? So this in the step of constructing this independent set, right? When you do this construction in each from each triangle, so from each class, you just select one literal that is set to true. So here you could in the third class, and maybe like s2 and x true, and x4 is also true. Then you just select one of these two vertices, like between x2 and x4.
I see. Okay, thank you.
In the chat, so what about string inputs? Do we use number of characters in the string? Yeah, indeed, we would use the number of characters in the string. So for string, I mean, usually we would assume that the alphabet is not too large, right? Maybe it's English alphabet, it would be like 26 characters. So that's kind of a constant number of bits. So the size of the number of bits that's needed to represent a string input would just be the same order of the number of characters in the string. So the length of the string. Okay, for questions of the form, prove that the problem A is in P if and only if problem B is in P. Does that mean we need to prove the reduction both ways? Yeah, so if and only if, then you need to show both reductions, right? Because if you just show that A reduces to B, then that just shows that the B is at least as hard as A, right? But that doesn't give you the if and only if. Does the two reductions only differ in showing the polynomial term transformation? Yeah, not sure about the question, but I mean, these two reductions could be completely different, right? I mean, I think in some of the reductions we've seen, it's like you can use the same reduction like for both forward and backward, kind of both say like from between independent set and vertex cover, like you can reduce like back and forth, kind of using essentially the same reduction. But for some of these problems, it's not true. Like last week we saw vertex cover to set cover. So there, like someone pointed out that some instance of set cover does not occur. So we cannot use the same reduction to reduce set cover back to vertex cover. So since we've already proved yes to A and yes implies yes to B and yes to B implies yes to A, but yeah, that's not sufficient, right? I mean, when we reduce problem A to problem B, then yes, it's true that we need to prove that a yes instance of A is carried over by that reduction to yes instance of B, and yes instance of B come from a yes instance of A. But then when we want to reduce B to A, maybe we need an entirely different reduction. It's not like these reductions are like the same construction, right? Like for yeah, just as I mentioned, like for vertex cover to set cover, the reduction cannot be the same reduction cannot be used to reduce set cover back to vertex cover. Yeah, so different reductions could rely on like different, totally different constructions. So this kind of proving yes of A, if and only if yes of B would if it would not be useful if you need a different reduction kind of. Yeah, let me write it down. So like A reduces to B. yeah, it's true that with the reduction, you need to show that yes of A, if and only if yes of B. But then suppose you want to show later that B reduces to A. I mean, if kind of the same like mapping between instance of A and instance of B work, like as the reduction, you can use the same reduction kind of again, then what you show about yes of A, if and only if yes of B would be useful. But it could be that here you need a different reduction. Potentially, you might need a different reduction. And if you need a different reduction, then what you've shown in the reduction from A to B about yes of A, if and only if yes of B would be completely useless, right? Because if the reduction is new, then you have to start from scratch. So kind of this yes of A, if and only if yes of B would not carry over. What's an example of a problem not in NP? Yeah, halting problem. It cannot even be solved in finite time. Yeah, I mean, as I said, like some problems kind of even, in these NP problems, yes, instance you can verify efficiently, right? There's a certificate, but for some problem, even like verifying this, even kind of verifying that a yes instance is indeed a yes instance, even that is hard. Like that is not in NP. But yeah, you don't need to know this kind of. Not gonna ask about problems. What problems are not in NP. Okay, so if there's no more questions, let me end here. Yeah, thanks everyone for the semester. It's been fun, and good luck.